of drainage and what is going to be happening. And there was quite a few comments after the event. There was quite a few emails and things after the event, which was lovely. Feel free to do that. I will put my email address in the chat if anybody wants it, just to ask questions afterwards. That's absolutely no problem. Today's then is to try and raise the awareness of scour issues. Now, I guarantee everybody will be aware of what scour is. You may not know it's called scour. You may not understand how it is and what it is. But you will have seen it. So the picture that's on screen at the moment, you will have seen that when you're down on the beach, these big depressions around structures. That is scour. So hopefully the idea is I'm going to give you sort of half an hour, 40 minutes, maybe, if I can drag it out a little bit, on scour. We're going to have a look at things like what it is. There's two main types: of river scour, or fluvial scour as we call it, just to complicate things. Or there's tidal scour, obviously coastal erosion, we've all heard of that. We'll have a look at the causes of those. The causes, the three causes of it, two of which we can do something about. The natural scour we can't really do anything about, but we'll talk about it. Again, we'll have a look at Network Rail's management process of that. We have got a standard. We've got a standard for everything else. We'll have a look at how we model and how we look at what's called sediment transport, which I'll explain what that is shortly. We'll have a look at some of the mitigations and the consents that we, the issues that we come up against with the consent authorities like the Environment Agency, Natural Resources Wales, SEPA, etc. And we'll have a look at some advancements. So there is a few advancements that's coming around, which are actually quite promising. So we'll go into that. So if everybody's okay, let's have a look at what is scour. If you look at Syria, who are the sort of national champions of this, the national experts, they say that is the removal of material from the bed or banks of a channel and from around structure by the action of water. So it's basically erosion caused by a water action. Now that could be tidal, it could be wave action, it could be just fast flowing water, it could be anything. But it's the removal of material from that location to somewhere else. That is scour. It is the most common cause of bridge failure. There's an estimated 60% of failures attributed to scour, but the hole itself, the scour hole itself, is not necessarily the failure mechanism. So that scour hole, when it develops, it might weaken the foundations, which allows some buoyancy to act on the structure. It may overtopple, it may turn. It just weakens the structure, and the actual mechanism of failure might be something other than the scour, but the scour has effectively caused that failure to happen. So that picture there, that is scour. That is exactly what scour is. You've got, I don't know whether you can see my cursor. David, can you just see whether you can see my cursor pointing?
Yep. Yes,
yep.
You can see that.
Perfect.
Yes.
Okay, so natural riverbed we can see is this level, and we've got a very deep depression down, which is caused by this bridge pier here. This one's a fairly obvious example of scour. You can actually see the foundations and the concrete plinth that foundation is sat on. All of which scour. I certainly wouldn't be that guy stood that close to a scour hole. You just have no idea what's going on under that bed. So I certainly wouldn't be stood there, but there you go, it's just me. So as I said, two types. So the first and the main one that we look at is fluvial scour. That is the erosion of a riverbed. You've all seen it on the sides of rivers where the trees start to fall in. The outside of a bend starts to get wider and wider. The good thing about fluvial scour is the flow direction is always constant. The river flows in one direction. You know, tidal scour, obviously it's multiple directions, but fluvial scour, one direction. There's a lot of things that affect the location and the depth of scour, and a lot of those things are actually within changes to the watercourse. Now that could be a landowner decides to install something upstream which diverts the flow, and it changes the whole flow characteristics of the watercourse. It could be that Network Rail's built a new bridge across the water. We've put a pier right in the centre, sorry, of the channel, and that's causing an effect. Pretty much anything that goes across the river or within the floodplain is susceptible to scour. How much it's susceptible is up for discussion. I want to give you a quick idea of the Tadcaster Roadbridge. I don't know whether any of you have seen this structure. Now, this isn't a rail structure, so I apologise for including it, but I thought it was worth a mention. Before I worked for Network Rail, I worked for JBA Consulting, who are one of the national experts in Scour. Now, this road bridge was approximately 300 yards from our office, and in the floods of 2015, granted they were very, very high floods, this road bridge collapsed, and there was an 8-metre deep scour hole discovered under the central pier. Now, that bridge was built in 1580. It was extended around about 1780. And when that flooded and collapsed in 2015, it didn't reopen until about February 2 years later. So you think, okay, that's fine. You know, the bridge has come down. There's a bit of a problem. The issue with this one is there's a 25-kilometre diversion route to get from where we're stood with that photograph to where the police van is over on this side. Happens to be where we're stood's most of the houses, and where the police van is Sainsbury's. So that 25-kilometre diversion is now looking a bit more serious, isn't it? A couple of things with this as well. There is a large weir just upstream. That was completely flooded and completely drowned out. What actually caused this? As I said, this has stood for since 1580, and it's never failed due to scour. A lot of arguments you get from the consent authorities, a lot of comments you get was, but that bridge has been there for years, it's never moved, it's never going to move. Well, that one 1580, and all of a sudden it collapsed. Obviously, we're getting more water. You know, we spoke last time about climate change and the amount of volume of water coming down our channels. This was actually caused by some debris buildup on the front, which blocked part of the pier, which we'll touch on later on in a different example. But I just thought it was worth showing you that, you know, the structure's been there for that long, and yet it's still susceptible. Tidal then, it's caused by wave action. We've said it moves in several different directions. It's quick to infill. Now, what that means is when you've got water flowing in one direction, it lifts the sediment up, it moves it out the way, and it moves it downstream. Now, there's no way that sediment can come backwards again and get in the hole it came from originally. With tidal movement, that can happen, and that does happen. The wave action, as the tide ebbs and flows, it lifts material out and it puts material back in. So they are quick to infill tidal holes. They're a little bit difficult to manage because when the scour is happening, unless you've got a camera or a diver or something in the water, it's very difficult to identify what is there, because by the time that tide relaxes and you get somebody in the water or a camera in the water, it looks like nothing's happened, but it could have opened up a 2-3 metre deep hole and then infilled itself. So it's quite difficult tidal. But the sediment's also a bit smaller. Obviously, we know in rivers we get cobbles, pebbles, boulders. In the estuaries and in the tidal environment, it tends to be silt and really, really fine sands, which is much easier to move than boulders. So tidal erosion is something that we don't touch a lot of in Network Rail. We do a bit, but not as much as we do fluvial. And we've got some pictures.
Iain, are you still with us? Iain, are you still with us? I'll contact him on the phone.
Sorry, there we go. We're back, I think.
Thank you.
Hello, hi everybody. Sorry, I did say I was in a cupboard originally. I apologise. So I don't know whether you can still see the screen. It says you can, so we'll keep going.
Yes.
So
okay.
Oh, perfect. So the picture on the right is, again, it's called coastal erosion, but essentially it is scour. It is a bank erosion caused by wave action, caused by water. So the Syria definition fits this perfectly. Now that part of the railway has actually just been reopened, I think, a few months ago, and that's took years and years to get that all back running.
Iain, we can only see one image on the presentation. I don't know.
All right, hang on. Let's try. There we go. Is that any better?
Yeah.
Yep.
There we go. Powers of technology. I feel like Harry Potter in this cupboard. It's a bit strange. Anyway, so yes. So essentially, this erosion here that you can see now is caused by wave action. It's water action. So let's have a look at the causes and the different types of scour. As we've said, there's 3 different types of scour. If I can get my machine working, there we go. So we've said it's generally caused by water action. Now that could be, you know, we touched on it, changing weather conditions, somebody's altered the channel, we've put something on man-made structure, but it could be natural variation. We've seen rivers that meander up and down. You know, a river wants to go in a straight line, and the river will naturally shift and change itself as it goes around. So the natural variation, when we're planning new structures and we're planning new railway lines, we're planning new assets, we've got to take that variation into account. We've kind of got to look ahead and find where that river is going to be in 30 years, 50 years, 100 years time. It's things that we really, you know, we understand now that we should be taking into account. So the 3 main types is local scour. That is directly because of something that we have placed in the water. I'll explain why shortly, but that is local scour. It happens only around the element that is in the water or close to the water. Contraction scour is something that's relatively straightforward, but that happens right across the width of the structure or right across the width of the channel. And it's caused because the channel is narrowed. Again, we'll touch on that shortly. And then you get natural scour. This is quite often called the conveyor belt scenario. So what happens here is, as the water's flowing down the channel, naturally material is rolling along the bottom of that channel constantly. But it's not just happening where our structure is, it's happening all the way upstream, all the way downstream. So it doesn't actually cause a scour hole necessarily, but there is a sort of conveyor belt of material. I don't know why I'm showing you with my hands because you can't see, but a conveyor belt of material that's sort of gliding along the riverbed. That tries to give you some sort of idea. So if you look at the bottom part of this rather than the top, because the top's a little bit difficult. So what we've got is the riverbank coming along in yellow. We've got the abutment, we've got the appear of a structure, and we've got another abutment. So the general scour in white is just happening. We can't do anything about that. That is just what it is. The contraction scour happens right across the width of the channel. That's the lighter blue. And that happens because we've reduced the area available for that water to flow through. The local scour and the pier and the abutment are because we've created vortexes. We've created a change in flow dynamics around the particular pier or the abutment, and we'll come on to that shortly. You'll get a better understanding of what that is. So we just said caused by a structural element, it increases velocity in the turbulence, and this is kind of the best drawing that I could come up with, really. I didn't draw this, I pinched this. Anyway, the flow is coming from bottom left and hitting this pier. Now this pier is actually a good shape. It's round, you know, it should allow water to flow around it, and it does flow around it. But what happens, because it's come across this blockage in the water as the water sees it, the water goes in all sorts of directions. So the water can go up, where you get this sort of standing wave, which I'll show you shortly. It can flow around the pier, which it does, but then as it flows around, it creates these rolling vortexes, which are just high energy water particles. You get rollers, so you get the flow hitting the pier and just diving down, and then they roll at the bottom and loosen the sediment up. They actually pick the sediment up and roll around, and you get this sort of teardrop shape. Looks like an aeroplane wing. And you think, well, yes, that's great in theory, and you know they don't really look like that, but you know in reality they do. You know, there's one perfectly. That could have been drawn because of that picture. You've got a nice shape. This one's actually perfectly shaped like a ship's hull, but there's still quite a lot of scour around the base of that pier. This is what I mean by the surface roller at the top there. Just a little word of warning: if you're anywhere near a bridge or a structure and you see a standing wave like that, just keep well away from the structure because you've got no idea what's going on underneath. That is a highly dangerous situation in terms of scour, and I certainly wouldn't even probably be stood where that person taking that photograph was. There's a video coming up next which will kind of highlight this point of that standing wave, so bear that in mind. Right, let's see if we can get this exciting scour video working. Let's see if we can press play. I've completely stolen this off YouTube, so I apologise, but it explains it perfectly. So what you've got, we've got a channel. The water is flowing from left to right as you see it. You should be able to see a clear circular cylindrical pier in the water, and they've used a sort of gravel bed. And what they're going to do is they're just going to increase Q is flow of water, flow rate. So they're just going to increase this, and we're going to get to see exactly what's happening on the base of the bed. So it starts off at 27-ish litres a second. And what we've got when we press play, very little. That's our pier, water level, gravel, nothing, happy days. So we've increased it from 27 to 35. So I'm just going to pause it there. So now you can start and see some little depressions in the water, some little bits of turbulence, but there's still not a lot going on at the base of that structure. We're going to increase it now to 42 litres a second. So now what we've definitely got some turbulent flow. And we've also got some little air bubbles. This is called air entrainment, which is another telltale sign. When you start and get bubbles downstream, you know you've got very turbulent flow. On this one, you'll also see some bits of material start to flow along the base of the bed. If you watch, you'll start and see some little bits and pieces just flowing around. We'll go again, up to 50 litres a second. So we've now got quite a lot of air entrainment. We've also got some particles starting to move. What the candle do now is they shift the camera position as well. So we're 57.7 litres a second. So what we've got now is the camera's slightly higher, but you can now start to see this standing wave at the front of this pier. And you get this hydraulic gradient, called a hydraulic gradient. So the water level is perfectly level. It rises and then it drops below the water level before it comes back up. Now that standing wave is significant. So if I press play now, you'll start to see quite a lot of material now start to move from the back end of that structure. We'll go again, 67 litres a second now. And now you can start and see there's an awful lot of material starting to move out of there. Now that standing wave, to me, is the signal that you've got scour happening at the base of that structure. I'm just going to rewind that one more time to 60 something, wherever it was. Quite a lot of sediment is getting moved from there. So hopefully that gives you a bit of a sort of real world look at what is happening. So that picture that I showed you earlier, if I can figure out how to work a computer, there we go. That picture there, that video you've just watched means that there is scour happening beneath that structure. Now, whether that is deep enough to cause a problem, whether that is there's protection on that structure so it doesn't matter, I don't know. You can't tell from that. So I would be nowhere near that structure if that was happening. Right, let's skip through that video and have a look at contraction scour. So this is literally just the narrowing of a channel. So we've said it before. If you want to think about it, think of what happens when you put your finger over a hose pipe. You don't turn the tap anymore. You put your finger over the end, you've reduced the area and you've increased the velocity coming out. Well, that's what happens to a river when we put a structure in it that's in the river. You know, the river width has not changed. The flow rate coming down has not changed, but because we've narrowed the area, the velocity of that river has to increase through that structure. And when you get an increase in velocity, you get an increase in energy. An increase in energy means the material can be shifted out of the way a lot faster and a lot easier. A very complicated and over-engineered drawing that you don't really need to know. General scour then is something that happens, as we said, it just happens naturally. It happens all the way along. It's just a conveyor belt as it's going along, and it happens the entire length of the river. That picture there looks ancient. It actually wasn't. It was taken by Jeremy Benn back in, I believe, about 1998. And the Environment Agency declared that structure was safe. Now, what you can see here is a riverbed level originally. We've got a really deep depression scour hole. These are the piles, which are the foundation. There's the foundation cap, and that's the pier of that bridge. But you can also see that the scour hasn't just happened here. That's natural scour that's happened all the way along the length of the channel. Frightening that the Environment Agency that the bridge was fine. Yeah, anyway. Touch on a few other areas of scour then. I know I said there was only a few types, but they all sort of fit into these. But these are things that we don't really take into account. So propeller wash. You know, think about what scour is. It's fast-moving water that has the ability to move material out of the way. A ship's propeller fires water out the back of the boat Therefore, that water is moving faster than it normally would in a marina. Therefore, there is going to be a risk of scour. The boat launch ramps often get undermined and collapse because a speedboat get launched. The first thing they do is open the throttle, and that washes away the under part of that boat launch ramp. So they quite often require a lot of works in there. Drainage systems produce scour. We've put this in a concrete channel. However, there'll be, you can see some scour and undermining of the wall there. It's moving water. It's what it does. Poorly designed culvert. I love this picture. It's not a Network Rail one. I don't know whether this is the upstream or the downstream. I have a feeling it's the upstream end of a farm crossing or something. This gate's a little bit worrying because it's a Network Rail colour, but there we go. And this is just poorly designed. We've got no we've got a pipe, we've got no head wall, we've got no smoothing walls, we've got no training walls, we've got nothing. The water just hits this and just rotates around. It can't go anywhere until it finds its way into the pipe. It's just poor design. And then there's poorly designed scour protection. I almost didn't want to put this in because this is a live job that I'm on at the moment in Wales. What we've got here is we've got a protected embankment. The railway line is across the top here, and we've got a river that turns 90 degrees, and we're stood in the estuary out in the River Conwy, I think it is. And we've got scour protection. That's great. We've got a concrete invert, hard invert through our structure and out in the estuary. Brilliant. What we don't have is what's called a transition material under here. And all of this hole that you can see is actually a scour hole caused by a poorly designed scour protection scheme. Now, in the top of it, you think, that's fine, we've got a concrete invert, but look at the damage it's caused downstream. That is a Welsh water supply pipe, and that is currently just dangling there. If we break that, we're in a world of pain. What we should have is a transition material. So you've got hard concrete invert coming through the structure. You've then got some rock armour placed downstream before it goes back into the natural bed. Now, the way this works is because we use Manning's value quite a lot in drainage and scour. Manning's value tells us the roughness of a surface. So if we've got a concrete invert, it's a nice smooth surface and the water can shoot across it, and it increases velocity as it goes across that. When it goes back into the natural bed, because it's stony, it's uneven, the Manning's value raises and the water slows down when it gets to this point here. So you've got fast moving water coming along through the structure, you've got slow moving water in the channel, and they crash into each other. And again, you get a lot of turbulence, a lot of energy. And what happens is that water starts to rotate and dive, and it starts to eat underneath the concrete. So if you've got no transition material here, you still get the fast water, the slow water, but it can't eat away at the rock. So you have to have that. It's poor design when you don't have that transition material at the end of a hard invert. So why do we need to bother? Well, there's been quite a few failures, and by failures we mean catastrophic failures. There's lots and lots of work orders around at the moment for scour repairs and scour infills and all sorts of things. And you think, well, yeah, 1846 to 2003, fine, 131. We didn't really know what we were doing in 1846. Okay. However, there's been 17 since 2003 up to 2013. There's been more since. Interesting fact. So these are the timeline of scour failures. In around late 1940s, early 1950s, we had a huge amount of bridge failures due to scour. Up 15 we had. I did some digging into this, and believe it or not, in the early 50s, the RAF started cloud seeding experiments to make it rain. Increase the volume of water going through the channels, increase the number of bridges that fail due to scour. Scary fact, but Google it. So let's have a look at a few different failures then. We're going to have a look at three. We're going to have a look at one in Ireland, which is Malahide Viaduct, which happened in 2009. We're going to have a look at Feltham, which also happened in 2009. And then we're going to have a look at Lamington, which you've probably all heard of, which happened in December 2015. So Malahide Viaduct, the RAIB report number is there if you want to look this up. Located on a beautiful, beautiful part of the world. It's an estuary, links Northern Ireland to Southern Ireland, I believe. Train driver reported a section of the viaduct that was collapsing. Obviously, all trains were stopped, and a couple of minutes later, this happened. It was inspected a couple of days before the viaduct collapsed, and there were no defects. And it's also had a scour assessment that somehow came up with not a high risk of scour. That's where it is. Beautiful part of the world, as I said, and you can see the location of the collapse. That is the historic drawing of that viaduct. So thinking of the things that we spoke about earlier on, Q equals VA, so flow rate equals velocity time, that's gone well, equals velocity times area. So we've got a nice big depth open channel coming in. We go through the viaduct over this mound, and we go back. What have we done here? We've reduced the area that water's got to flow through. We reduced the area, we've increased the velocity. So the velocity of the water going through that weir is phenomenal, and that's caused that to happen. A couple of things to note on there. How brave this guy is. Stood right up close to the edge of it. And why has that guy not got a hat on? We'll skip on. Feltham. Interesting one, Feltham. I've done quite a lot on Feltham, and there's a number of reasons why, and I'll explain as we go along. So in 2009, a member of the public took this photograph. Doesn't look too much like anything, does it really? Railway runs across the top of that structure, and there's a couple of twigs and branches and things that's on here. Fine, no problem at all. Local fishermen, however, reported to the Environment Agency that where they were fishing, the water depth had increased by over ½ metre. So there's got to be a blockage somewhere to cause that water deepening back upstream. No problem. Amy Rail went and had a look at that structure on the 2nd of October, found nothing wrong with it, no defects. On the 28th of October, the Environment Agency finally getting around to those local fishermen reports, they went and took this image. Same bridge, a couple of months later, and it's gone from a couple of twigs to a significant amount of debris that's now blocking that structure. Now, what you can't see on this image is any water going across the top of that debris, which means all the water is now going underneath that debris, the flow rate. And as with Malahide, what we've done is we've reduced the area, therefore we've increased the velocity of the water that's going under that structure. 14th of November, there was a 5.5 metre scour hole discovered. And it was discovered because the 2237 train reported a track dip. The line was closed, and 6 minutes later that happened. Now, it's all started with a very small amount of debris that's across that channel. Something that you would walk past if you're doing bridge inspections or you're out and about, you'd walk past and you wouldn't think twice about. You just think, oh, there's a log there, or there's a bit of debris. Because I'm a geek, I always report it if I see it. I'll phone the local council, I'll phone whoever, because I don't want to have seen a bit of debris on a bridge and then to hear about it collapsing a couple of weeks later thinking, if I'd have reported that, that might have been saved. First picture was scary. That picture's looking from track level. I don't know who the hell took that picture, and I certainly don't know who took that one. But that looks down onto the river. Yeah, frightening. So, Lamington. Again, interesting one, Lamington. You probably all know the backstory. This I'll skip through. So New Year's Eve, there was a track defect. There's a dip in the track. You can see from the arrow that says dip. Put an emergency speed restriction on. The following trains crossed under that. Maintenance team deployed, and they didn't find anything wrong with it. The maintenance team waited till the next train, the 840, passed at high speed, at track speed, and they observed very large movements in the track, and they then shut the line so they could figure out what was going on. And it was determined that a pier had collapsed underneath by train movement vibration. It was pier 2 that collapsed. Obviously, we've got a missing block, we've got a few vertical cracks, we've got some fractures, we've got all sorts of things. We've got a displaced bearing plate. Lots of things wrong with pier 2. Okay, so that's pier 2, cunningly labelled pier 2. And what they've done is we've created this lovely pontoon, I guess, to get out, get the excavator out, so we can create a dry working area so that we can work around Pier 2. That's great. However, as all of you now know on the call, because you've been listening intently, I'm sure, what have we done with this channel now? We've gone from that width to this width, Q equals VA. We've now increased the velocity through these parts of the structure. So what happened then? Pier 3, this pier here, then starts to collapse 4 days after we put that pontoon in. And that's the pier we were working on. That's the pier that collapsed, and the line of the channel used to run down here, and all of this is now scour damage. How big are the drivers? Yes, to be sat in that excavator over that hole. Wow. But that was all caused because of that pontoon. The original damage was not, that's fine, but the way that we tried to repair that caused a problem. That was 2016 when we understood scour a bit more. So it's not something that you think, well, we understand it now, the problem goes away. It doesn't. It still requires people who understand scour to look at some of these schemes and look at these repairs and be involved in the methodology before we start going blocking rivers off. So we do have a management process. It's called Civ 295, and it essentially gives us a two-pronged attack to figure out how much at risk our structures are of scour. So we do a stage 1 assessment, which is a very, very high level assessment. If it comes back as possibly high risk, we then start to get hydraulic modelling done. We get coring done to find out foundation depths. There's a lot of assumptions going to the stage 1, and there's a lot of fact that goes into stage 2 to try and confirm or update the score. We then get a final risk rating, and that then gives us an option of we can monitor it, we can remediate it, or it gives us options of what we want to do. The priority scores range from 6, which is pretty low, through to a priority 1, which is, oh my God, get somebody in the river and do something. The priority rating at the moment, we are anything 16 or above, then we have to permanently reduce that score. That's an ORR requirement. In CP7, when that starts in a year or two, it goes to 15.8 or above. We have to remediate, we have to permanently reduce that score. So that currently puts us anything on a medium risk. We now have to do interventions on when we move into CP7, which has cost implications, obviously. The remediation options, monitoring, could be some engineering works. There's a myriad of things that we can do to actually mitigate scour. We do some modelling, so there's some hydraulic modelling going in. It's not particularly in-depth or extensive hydraulic modelling, because all we really need to know is the flow direction and the velocity. And we need the velocity at the base, the bed, because that's where the scour happens. So we use something called HECRAS. It's a free piece of software. You can download it if you wish. There's lots of YouTube videos that show you how to use it as well. It's an American military developed piece of software, and the American government have basically said it has to be free for life. So we use that, and it's industry standard, to be fair. So we could do a 1D HECRAS model, which is what we'd normally do. As I said, it gives you flow velocity, gives you water depth. That's about it. We could up that if we needed a bit more detail or a bit more information. We could use a 2D model. So that now gives us things like flow paths. It now gives us things like floodplain monitoring, etc. Or we could use the CFD 3D fully singing, dancing model, which we'll come on to in a few minutes. The information required, well, we need some dimensions, so we need a topo survey. Ideally, we'd get some cross sections of the riverbed so that we knew what shape, how wide, how deep that it is, and we need some what's called initial boundary conditions. So if we're going to run a hydraulic model, you need to know your starting point of what the flow rate is. So then you'd look at your hydrology, you'd look at how big the catchment area, how much water is going to come down that channel. You could have a look back through previous flood event data and run a particular scenario, but we let specialists deal with all of that. That's far too complicated for us to worry about. Looking at velocity and water depths, the impact that a structure or an element has on the water, it's widely regarded as you look at what's called the effective width, so twice the effective width of the pier. So if you're straight on, if the water's going straight onto the pier, 90-degree angle, perfectly on it, you'd go twice the width either side. If it's on an angle, then you'd kind of look at what the water sees, you'd go twice the width either side. It is going to be a quick look at Hecras. There it is. That's it. No, I'm kidding. So it's a very basic program, but it's very clever with the programming back end. So the blue line is the water course. The green lines are the topo surveys where they've done some cross sections for us. The red dots that you can possibly see are where the modeler has said that is the top of bank. So normally the water would be contained within those two red dots, and the extension of the green line is a floodplain. So it shows it on this quite nicely. That's the bridge. You can see the red dot and the red dot, which is top of bank. The water would normally be within those channels. If it falls out of that channel, we then know it's on the floodplain. I won't get too bogged down with Hecras. It's a whole minefield all on its own. So we've figured out we've got a structure that's a high risk. We've figured out we need to do something. Obviously, you know, we can't just decide to go in a water course and do it. There's consent process. There's third-party people that we need to consent with. If it's a main river, it's going to be the Environment Agency. It's going to be Natural Resources Wales. It's going to be SEPA in Scotland. If it's a non-main river, if it's only a little tributary or something, it's going to be the lead local flood authority. So it's going to be the local council. Two very different ways of getting consents. Environment Agency, NRW, etc. will require lots of drawings, lots of methodology, and they'll be very interested. The local authority will be less interested in the design and more interested in the check that you were going to write for that consent process. If it is a main river, it's going to require something called a Wfd Assessment, which is a Water Framework Directive Act. That can be a very expensive piece of work to get done. It looks at all sorts of geomorphology within the river. It looks at water quality, it looks at environmental, it looks at ecology, it looks at lots and lots of impacts of any works that we are going to do. So obviously, if you think about the logistics of working in a river, we're going to put an excavator and we're going to start digging around. We're going to move an awful lot of silt, and as part of that, we're going to dirty the water downstream. So we need to be sort of careful of what we do. So the consents, you know, they're responsible for water quality, they're responsible for ecology, and they can't have us, even though we are Network Rail, they can't have us just going in doing what the hell we want in a river. We do require consent for permanent and temporary works. The temporary works one's generally harder. Permanent works, the permanent state is normally acceptable. It's the methodology of how we get to that point is the tricky one usually. The no barrier to fish migrations are a biggie at the moment. A lot of the works we do are on rivers where salmon can get up to spawn, so we're not allowed in within fish spawning season at all. So there's quite a lot of fish-friendly pumps that you can get where if you need to overpump a river, the fish don't get minced as they go through these things. There's all sorts of stuff that we can do. The hard invert that we saw at the Mill River one, where we've got the Welsh water pipe, they're generally now frowned upon because they tend to cause more problems than they solve. They're kind of trying to push us down soft engineering routes, which I'll come on to, but yeah, it's a strange one at the moment. They don't like us pouring concrete in a river. I don't know why. And we used to get a high risk structure. So maybe, I don't know, Pier 2, for example, might be a high risk. So we would protect the whole asset. Nowadays, we're not allowed to do that. We can only protect what is at risk. Now, the problem with that is if we protect a part of the structure, we then need to look at it because we may have moved that risk to another part of the structure. So we need to sort of think about that as we're designing. So some mitigation, rock armour, we've all seen that around. Varies in size between sort of tennis ball size up to VW Beetle car size if you're on an estuary or a tidal lagoon. We can get these rock rolls, which are like gabion baskets. Just don't, they're terrible. Concrete mattresses, these are quite popular. So what these are sort of a geotextile that's zipped into to shape around the structure, and then a concrete pump truck is parked somewhere near and it's filled with concrete. Concrete hardens, goes off, and you've effectively got a concrete invert. But if you notice, it's shaped. It's not a smooth surface, and the reason for that is because we don't want that water to increase velocity. We want that turbulent flow. We want the slower water through the structure, so that when it does get outside the structure, we're not getting that undermining. It's also given us some oxygenation in the water, which is going to help the ecology. It's going to help the fish. We've got gabion baskets, similar to the rock rolls, don't bother. Or we've got sheet piles around bigger structures. Somebody working hard there on his phone. I love spotting these things on photos. I'm terrible for it. And then we've got, as we've said earlier on, the concrete invert. So that's very straightforward concrete, pour some reinforced concrete, some 393 mesh or whatever it is underneath it. But you have to have that transition material, otherwise you're going to get damage. So some advancements. We've got a few R&D projects that we're currently on with. We've got some real-time scour monitoring. That's happening in Wales. There's a few sites, 3 sites around the UK. We've actually co-authored a paper on this, which has been published on the work that we've done on this. And we're going to the International Bridge Conference in July. I say we are if my boss signs the paperwork, because it's in Barcelona and he doesn't want me to go. We've got 3 different types of sensors that we're testing there. So we've got some sonar sensors, we've got some vibration sensors, and we've got some electrodes. The electrodes are my preferred option. They measure the relative permittivity of the ground, and they can tell the difference between strata, water, or a mix of the two. So you get a very nice graph that shows you exactly what's happening. This is kind of what's happening here. So these are, if you picture a scaffold pole, drive the scaffold pole into the bed where you think the scour is going to happen, and then put your electrodes or your vibration sensors inside that pole, and that's how they work. So this is the relative permittivity one. It knows saturated soil, it knows water, and then it knows deposit soil. So you can see which sensors are then exposed to water. So you can then keep a track of how deep that scour hole goes. If anybody's interested in that, please talk to me separately. I won't bore you too much with all of that. Probably the biggest advancement though is this 3D CFD modelling. I know I touched on it last time, but it really does help. And I'm going to give you a bit of an idea of what's going on with that CFD modelling. We were approached by the Australian government. This is in my previous role, and they said, and I kid you not, they said, can you please model this bridge and tell us what happens in a flood? And they sent us those 2 photographs. So we did a lot of Googling, a lot of Google Maps, and we built this in CFD. Ran the model. A couple of things to note. There's some graffiti that's just on this corner edge that you'll need for a couple of slides time. So bear that one in mind. What happened was we put the flood down it, and this is the bridge, and we saw that the water was overtopping that bridge. Now it's 12 meters high, that road bridge. So we thought, oh, something going on there. That's not right at all. You know, you've got quite the water's all coming all the way out the channel. You've got these real high vortexes right at this abutment where that graffiti was. It just doesn't look right. There's something just not right. So we sent it back and we said, okay, this is what it's showing with the basic information. Can you please provide some further information so that we know we're on the right track? And they sent back this photograph. So that is the same road bridge, 12 meters high, and it's overtopping. And they basically went, no, that's exactly what happens. Carry on. Tell us what else happens, please. So they can, apologies about that. So we can, you know, see what's going on. So we ran the model again. So what we've got now is this is the left-hand pier, right-hand pier, sorry, where we've got the graffiti, and it shows that we've got massive scour at this front corner, and we've also got some scour over on the other bank. So again, inside of a bend, you don't expect there to be scour on the inside of a bend. So again, back to Australia. Okay, can you give us an idea of what's going on? Because, you know, that doesn't look right on the inside of a bend. And they sent us these photos. Note where the graffiti is, and the now missing abutment of where it's all scoured away. And then further downstream, exactly where we showed it, is the rest of that scour. Now that was done with literally a Google Maps image and some very basic dimensions off Google. And it proved a concept that actually CFD modelling does show scour. It shows where it is, it shows how severe it is, it shows how deep it is. And as part of that scour monitoring program, we've actually used CFD model in all 3 structures to locate where we put the sensors, because we're that confident that this CFD modelling tells us exactly where scour happens, that we've actually put money on it and we've placed these sensors in the ground and they are live monitoring now. Just to give you an idea of what the scour looks like, this is also an Australia project, and what they have in Australia, if you've ever been, is they've got these big flood relief channels. And now these run down onto the beach, and all of the flood waters within the town just come roaring down these and they outfall into the sea. And the Australian government said, well, that's great, but what happens is they clog up with sand. As the tide comes in and out, bed deposition, as we've said, it drops sand on here. And we currently pay a guy with a shovel to come and clean all this out. Is there any other way that we can do it? So we looked at this and went, okay, how about you split your gates into 2, you hold a bit of water back, and then you open one of the gates and effectively deliberately scour that sand away. Now, I don't know whether this is going to work, but we'll try. Doesn't look like it. I will attempt to share that another way. 1 second. I'll attempt to share. I'll do the summary and then I'll come back to that. I'll attempt to share that a different way. So we've touched on, we know what it is. It's the removal of material and it's caused by water. It could be tidal, it could be wave, it could be a propeller, it could be drainage, it could be a river. There's 3 different types. We have got a management process. That management process is worth saying, by the way, is currently under review. We're trying to get the 3D CFD modelling written in as a stage 3 assessment, which hopefully will be coming shortly. The mitigation should be site specific and it should look to improve the environment. It should look to improve water quality. It should look to improve the ecology. It should look to improve the area if we can. The modelling is key, because if we don't get the modelling right, then we're not going to get the protection measure right, and it means that bridge could possibly still be at risk. And the advancements, they're very exciting, and they are coming along, but it is going to take some time. Just before we do questions, I will stop presenting that and I'll just try and present my screen and show you that thing. 1 moment. Let me see if I can share the screen the old-fashioned way. Hang on. Can you all see that still?
Yes.
Yeah, perfect. Okay, this should work then. Okay, yes, it does. So quick back, sand channel, open 1. So if we open 1 channel and we flood it, you can actually see the sand scours itself away. This is real time. So to clear half of that channel takes just over 120 seconds. That's how fast scour happens. One of the things that always astonishes people when I tell them is that when we do have a flood going down a river, the scour hole opens up and is its deepest within 10 or 15 minutes of that flood happening. After that, it's filling itself slowly back in, because you know the flood can move an amount of material, but when it's at that velocity and that energy, it moves it very quickly. So there you go. Thank you for your time. Have we got any questions? We've got about 8 minutes, I think, David.
Yeah, there's no questions in the chat. Is it anyone want to raise any questions? First of all, Iain, thanks for presenting again. Maybe not a normal presentation that we have on the PWI, but it's extremely informative, and yeah, I know the cloud seeding and also this this risk of moving the risk when you're dealing with the bridge scour scenarios. Would anyone like to? Mr. Tomlin's saying it's a great presentation. I've got a hand up, just bear with me. Matt, you got a question?
Yeah. Hi, Iain. Good to hear from you. It's been a long time. I was just wondering whether there's any a program of work to look at bridge foundation depths, because one of the key factors in the scour assessment scoring is the depth of the foundation. And from my previous experience, we've never quite got that right, and they're quite often deeper than what we show. So you can get artificially high scores. which could be driving up construction costs for no reason. I think that there could be a significant saving across the whole Scour programme by spending some more time doing GI at the structures.
Yeah, hi Matt, how are you doing? Yeah, it's something that we've had the University of Bristol and the University of Exeter doing. We've done a full Civ 295 review, which is currently with the Technical Authority and Steve Roth at the moment. And part of that was to look at things like how we determine foundation depth. So that review is ongoing, and hopefully we'll have some, well, fingers crossed, we'll have some results shortly about a way forward. I don't know whether it'll be an answer, but it's certainly been looked at, yeah. Agreed.
Okay,
When the CP7 mandate comes in around all structures with a score of greater than 15.8, it would be worth taking that list of structures and doing your investigation that way, wouldn't it?
Absolutely, and that's, as I said, that's all in the pipeline at the moment, which is sat with Steve Roth and the Technical Authority. So, yeah, it is, and I think that 15.8 is going to cause us. It's not going to cause us a few issues, but I think it's certainly going to cause us a few questions, and we're going to start protecting structures that maybe we really don't need to. But we'll see how it goes.
Cheers.
There's a question in the chat, Ian. I don't know if you can see it, so please forgive me getting it wrong. Jim Tinney, any experience in the use of Renault mattresses or similar for the transition from the hard bed to the natural bed, moving away from structures?
Absolutely. Reno mattresses are used actually as scour protection themselves. They're not just used as transition material. The problem is they're essentially a buried gabion mattress. They're a buried gabion basket. So when you get debris and very large material moving along that river, that intertwined metal frame, the cage, is very prone to damage. If you think that, we might bury these things 200 or 300 mil under the riverbed. During a flood, that 200 or 300 mil of riverbed is gone, and the mattress is exposed, the metal is exposed, so you get debris coming down, it just smashes it apart. We've just had a structure in Wales near Aberystwyth called Blackbridge, where we did the same thing. That there was a Reno mattress under there, but the amount of damage, the Reno mattress uses very, very small stone, and it's the cage that contains it. And so as soon as that cage goes, that material can be washed away very, very quickly.
Yeah, so is there a preference for sort of just larger size stone subject to the sediment transport calcs and no containment for it?
Yeah, that's the idea. I mean, if you speak to the people who make Reno mattresses, they still tell you it's better than rock armored because it's more transportable, it's easy. And the original one in the River Reno in Italy is still there. Well, it might be. But the ones that we've put in for Network Rail probably aren't, because they've been smashed apart by logs or other things.
Sure.
So yeah, it's preferable, if you're going to put rock in, just put some big stuff in.
Interesting, thank you.
Okay, well, thank you very much, Ian. I don't know if people attending can unmute themselves, and but yeah, really good presentation, Ian. Hopefully that we can put that on the YouTube site. We'll probably just double check some of your references, and then that can join the previous presentation that you provided. Really gives us a general overview for drainage in general, risk water management, as you've said in the past. So I don't know if colleagues can unmute themselves, if that's possible, and I'm looking for a round of applause, or cheers, or was it just a really clapping?
Thanks, Ian.
I'm sure there's a better way to do this, but there we go. Okay.